Next up, we have Professor Loren Frank from UC University of California, San Francisco. He's been working on building a kind of integrated prototype approach to integrating NWB and DataJoint together, working on this the third style of integration that Tim mentioned in his presentation.
All right, thanks, Brian. I imagine all of you, well, it's late in the day for you, early in the day for me, and I can imagine you're running out of steam. So I will try and make this sort of high level, but please feel free to interrupt me if you have any questions, and we'll see how it goes. So I just wanted to start a little bit with, I mentioned this in the sort of talk that I recorded that I'm guessing many of you watched, but what's the goal? So, you know, having been doing this for 20 or some odd years, the problems that one runs into are data sharing within and outside the lab, and this issue of flexibly querying and getting access to the data. And so I think we're finally at the point where we can solve those problems pretty well. And it's also, I just wanted to, in the context of this, thank all the folks who've made this possible, Ryan and colleagues, Ben at working on NWB, Tin and Dimitri and others at DataJoint who helped build a lot of the sort of basic tools that are required to make this happen. Alessio and others at Spike Interface, because thanks to them, this can now be integrated there. Our goal is to say, how would we maximally standardize things across labs and across groups? In this case, this is for my lab, and so again, this is a lot of the things that Tim just talked about, but with, I guess, a slightly different approach than was presented. So let me just get started by sharing my screen. I'll just start. This project is available. This is the repo. I'm actually not sure you can read this, so you can read this hopefully. It's called NWB DataJoint. It's open, so you can clone it or grab it or whatever. We're still updating it, but within here, I'll just go down, and sorry, let me make this slightly larger. There is a notebooks directory, and this is what I'm going to be running today. There are tutorial notebooks, a populate tutorial, an LFP tutorial, and one for interfacing with Spike Interface. These all work, and thanks to Ryan, we have a nice small sort of test data file to run them with. Again, if this is some things that people are interested in, please feel free to take advantage of this, take it, do pull requests or change things as you see fit, because that's the goal of this process. So I want to start with our approach, and our approach here, and again, I hope this is visible. Please let me know if I should make it bigger, because it's hard for me to know what comes through on people's screens. So is this visible to people, or should I make it larger?
I can see fine. Thanks.
Okay, thank you. Appreciate it, Tim. We started, and we actually worked with a company to do this, but Ben Dichter has been very involved in this, is we wanted to start, and immediately after our data acquisition, which is complicated, kind of like Kenneth's question before, put everything into a single NWB file. And I think that's really important from my perspective, because once you do that, any tool that anyone builds that works on an NWB file suddenly can work on the data that you have. So what we have is this YAML file with basically all of the various data that we need to go into the NWB file. We have a bunch of extensions that we've developed, like associated files. And this is really trying to get at that problem is, we also have complicated multimodal data. So we have electrophysiology data at high rate, we have digital IO data, we have sensor data, we have video data. All of those things go into this single NWB file. We have things where we can specify what cameras we were using. This is all still in process, which is why these are unknowns. We have task descriptions, which say what was the animal doing, which camera was being used, which epoch of our data were we collecting this in, video files that might be associated, behavioral events, so which digital input and output corresponds to which behavioral event in the file. And then finally, we also have electrode groups. In this case, these are tetrodes in the hippocampus, and these are NWB objects that I think probably many of you are familiar with. And we have a way of mapping those back to the original devices that were used with some new extensions. And again, all of this is open source, so if anyone wants any of the details, let me know. But the upshot is, with this single YAML file, you can run a program called rect to NWB, or it's in a rect to NWB repo, and I'll post that later, that produces one NWB file for a day of data with all the raw data in it. And at that point, that is all we need. And this, getting to Kenneth's question, if you have this file, you can imagine a GUI that would help populate this, and we're working on that now. That file becomes everything, all the metadata that's required, and because it goes into NWB, it's by definition standardized at that point. And I really like that idea because it means that if I wanted to ever share the raw data, you know, normally we don't send 100 terabyte files around, but if we wanted to, we have it, or we can share products. All right. So, and again, please interrupt me. Oh yeah, please, question?
Yes. Just asking about this one file thing. So do you actually, I guess you first record these huge data files, and then do you basically duplicate the data to put this into the one file and then delete the old file?
Great question. Yes, we do, with the idea that we can then get rid of the other data if we need to. The problem is what we actually did before this was to split out our raw data into many sub-files for things like spike sorting. And the problem is that every data acquisition system has its own specialized format. And until the data acquisition system developers get to the point of writing data out in NWB, which I think might happen someday, but we're not there yet, we didn't have a way to not duplicate it. That said, it's a one-time duplication, and then, as I said, we can get rid of it, so it's sort of manageable, but definitely something to work on. That okay?
Yeah, thanks.
Okay. All right. So then what we've done is develop a DataJoint schema, right? This takes advantage of all the stuff that Tin talked about. And this is the package. So this is the file. It's called the populate from NWB. Again, I would love it if people tried this out. There's a Dropbox link here to a 2 gigabyte file. So this is a very trimmed version of one of our sort of test data files. And I'm just going to take you people through this. Again, please ask questions about what's going on, if that would be helpful. So we start with basically simple things for a Jupyter Notebook. Those don't really matter in this case. We say, where are the NWB files located? And then, so that's this environment variable, the NWB DataJoint base directory. And then we're also working or playing with something from someone named Jeremy Magland, cachery. You don't need to worry about that right now. We then import the two notebooks, the two packages, NWB DataJoint and DataJoint. And then we run one command, NWB insert sessions on this NWB file that we've created, which, needs to live in the data directory. And it populates all of these schema. So this also gets back to Kenneth's question. This is automatic, thanks to all the great work that DataJoint does, where it creates all of these different schema, taking data out of the NWB file and putting them in DataJoint. And the idea here is that this is in some way duplicative, but we're not putting any raw data into DataJoint. This is only metadata. So that means we can take advantage of DataJoint's ability to do searches and organize things and maintain the structure of the data, but we don't copy raw data ever into the database. And I think that's really important. Databases are usually not great with big raw data files, although they're getting better at it. But it means that we keep the raw data in the NWB file and we don't duplicate it again, sort of getting back to that question. So, for example, this is sensor data and so on. And so what I'm going to do now is just show you what this looks like within the DataJoint tables created from this NWB file. So this is the first thing. When you run the NWB file is the name of a schema. This is just a Python class, basically a Python function. So you can run it and it will show you what's in the DataJoint table. And so in this DataJoint table, the NWB file, which is kind of the base because every session is one file, we have the name of the file and then where it's located on the disk. And this is what allows the other parts of the code to go get stuff from this file when they need it. Then, as it says here, each NWB file defines one session. So this would be 1 day of recording for us. It could be whatever it is for you. And this has all the information that we want, the metadata about the subject, the institution, and so on. Let me actually make this slightly larger just to make it easy to read. So again, if you saw Tin's presentation, there's dependencies between these schemas. So this session depends on an NWB file, and that's what's indicated in black here, that's what's called the primary key. So this is this says this is the NWB file, and that's how I'm going to define my uniqueness. And then it has a subject ID, an institution name, and all of these other things. One other thing I'll mention that we think is really important is we are referencing all times to the beginning of Unix time. So this is when the computer era started, according to Unix people. The reason for this is that we want all times to be absolute, which means we can always reconstruct what time of day something happened at. We know what order sessions happened in, and this just gets rid of lots of problems of figuring out when things happened if you have relative times. So all of our times are since January 1st, 1970 in seconds, and that turns out to work really well for being able to concatenate things across days or plot them in any way you want to. So I strongly recommend that as an approach. You know, if you're at that point where you can sort of start with this. Obviously, I know how difficult it is to re-engineer things, and I'll just say this is completely re-engineering what my lab does, and it's painful for me and everyone in the lab, but I'm very convinced that it's worth it. Okay. So we can then use this diagram method, and this is something Tin talked about just to visualize this dependency. So here's the NWB file. It's in a green box because it's basically imported. It's data that comes from, or rather it's data that's sort of manually inserted. And the session itself is populated. That is, it's created sort of by this populate command in DataJoint. All right. And again, please stop me if you have any questions. So we can then just to give you a sense, what we can sort of diagram a bigger chunk of the thing, which is the session, which has references to a subject, because a subject might be in many sessions. There's one NWB file per session, that makes it unique, but there's also an institution and a lab. And so again, what we're just doing here is taking what's in NWB already, this important metadata, and linking it to each session so that if you wanted to do a search and say, I want all the things from my lab or all the things from this institution, that becomes really trivial to do, again, thanks to the DataJoint work. Okay. So that's the basic structure, and I'll take you through a few more things, and then I'll show you how we can actually use this to do some computing. So within this, we have different schema. In our case, we have this one called raw. This is the raw electrophysiology data. In this case, it's 30 kilohertz sample data for several hours. And this schema, or this table, has, again, it depends on the NWB file name, because there's one chunk of raw data per day. It has an interval list. And this is another thing that I think is really important for anyone doing analyses of neurophysiological data. Everything we do, with very few exceptions, so almost everything, involves looking at things in chunks of time. So there are chunks of time when data acquisition is going on, there are chunks of time that define trials, there are chunks of time that define perhaps behavioral states, whatever it is. And so built into this is this idea of interval lists, that is sets of start and stop times that define chunks of data. And so every bit of data, of course, has a corresponding set of intervals or an interval list, which makes it really easy to then know what times are defined, and you can union or intersect these interval lists to figure out exactly which sets of times you want to analyze. And because those are carried with you, you always know what times you used. So this is, I think this is critical for doing the analysis well, and being able to refer back to this is really useful. Okay, the other thing this has is this object ID. So this is a UUID string, something added by NWB folks, so thank you again for that. This provides a really simple way of going to the NWB file and saying, I want this data object. So you don't need to know what it's called. You don't need to know where it's stored. All you need is this object ID. And I'm sorry, I don't know whether you guys have looked into that, but I can just say basically NWB objects this thing, and poof, it comes back to me. And then of course, things like the sampling rate, comments, and so on. So what does that mean? Well,
Sorry, can I?
Oh, please, yeah, please ask.
I think, yeah, we just had a question in the chat, and this was also my question, and I think this object ID gets to this. So does this mean it's kind of independent of where the data is stored? So as long as you have this object ID, if you move around your data, something else takes care of how to find it.
Yeah, yes, absolutely, yeah, right. So if you move around the data within in the NWB file, you have to choose what containers and things to store it in. So this basically just gets rid of all that, so you don't need to know anything anymore. So yes, but it's a really good point. Again, the goal here is to make this as easy as possible for users, so they don't need to understand the microstructure of files. right? They don't even need to understand NWB at all. They just need to be able to work with the individual data objects. And I think that works reasonably well. And then I'm sorry, I didn't realize I wasn't watching the chat. So let me just answer. So if you have more than one NWB file, so there's two approaches to this, and this is a really good point. So as Tin mentioned, you can have DataJoint do all of the file storage for you. And we started out with that. And the only reason we're not doing that is because we're trying something else with Jeremy Magland, where we have something called cachery, which is basically a file storage and file retrieval system, where it doesn't matter if you move the file because the files are referenced by their, basically by their characteristics, by a, what's called the hash of the file, so that you can find the file anywhere and it doesn't matter where it is. But also, as Tin mentioned, you can, for example, put this in DataJoint, and DataJoint can manage it for you. So there's a bunch of solutions there. I guess, one of the challenges always, what happens if you move your raw data and don't tell anyone about it? Well, you're in trouble, right? So some level of this is important, but the other thing that's important here is the users never need to do this. As soon as they put the raw data in, they never ever need to touch that directory again, and everything else can be managed here. So I don't think this will turn out to be a serious problem. Anyway, that is, I think, solvable. But yeah, please keep the questions coming, and I now have the chat open, so I will see them if you don't want to speak up. Okay. So, all right. Okay, so what I wanted to show you here then is this is what this looks like. We have a session, and that has raw data attached to it because the session becomes the primary key for understanding the raw data. And then we also have this interval list, which again defines the times when the data are valid. And I explained why I think that's really important. Okay, so now let me show you what happens if you want to grab the data, because this is the thing, of course, the structure here is only for our ability to do something with it. So this is where the DataJoint abilities become great, is you do queries on the data by taking the schema and ending it basically with what's a dictionary. Now, I don't know how many of you know Python. So all this is a set of matching things where you say, I want the NWB file name to match this string. So give me all of the rows of this table where the NWB file name matches this string, right? So again, kudos to the DataJoint folks. This is, I think, as simple as it could possibly be to be able to get a particular chunk of data, which is great. And then also they developed this function called fetch NWB, which is specifically designed to deal with NWB files and get things that have an object ID in them. So here, I'm running this fetch NWB. I'm getting the first element that it fetches, which in this case, there's only one element, but fetch NWB is designed to return many elements. For example, you might want to run many data files at once. So that's straightforward. And so here's what this raw data object looks like. So it's a dictionary where you have all of the entries in the raw data. Here's the file name. Here's the interval list name. Here's the raw object ID, and so on. And when you do fetch NWB, so this is just a printout of it, you get this raw object. All right, so this raw object is an NWB electrical series. So it basically gives you a pointer, if you will, a reference to this electrical series. And now I've got the data, I've got the description, I've got the list of electrodes it came from, and so on. So I really like this because it means that if anyone has written something that works on an NWB time series, I can just pull up the time series and I can use it. It's always in a common format, so the users can't screw that up. They can't change it. They can't mess with it. This is the raw data, and it has all of the elements that you need, and then you can do things with it. And I'll show you that in a little bit. Yeah, we have time for that. All right. So again, there's some little notes here just trying to make this more tutorial-like. But this is, I'm very, well, as one often is, enamored of one's own work. Since I've actually been working on this myself, I really like this, and I'm hoping that I'm not deceiving myself in this, but I just feel like it's going to make people's lives in my lab and maybe elsewhere a lot easier in terms of being able to get to the data quickly and easily. Okay.
I have one more question.
Yeah, please.
About what you just said. You said, so you like it because the users cannot basically screw with the data or something. Is that okay?
They can't screw with the raw data. They can do anything they want to analyze it.
Yeah, so what do you mean with this, and what is the alternative? So yeah.
Oh, I'm sorry. Yeah. So basically, the way NWB works is you can get rid of objects in a file, and we use that later, but you can't change what's in the object. And the way DataJoint works is that you can't change individual elements of a table. You have to delete that element and get rid of it. So basically, the goal is to prevent, it's easy to make mistakes if people start substituting things in and out, just because people make mistakes in their code. And so both DataJoint and NWB have sort of a structure that means you can't substitute things in and out easily. You really have to sort of start over. And so I just think that's really nice. Not that this happens that often, but it provides a very clear structure of, look, here's the raw data, do with it what you will, but nothing that you do to this thing will change the data on disk. And so, you know, it's kind of like, unlike a MATLAB file where you could easily resave it and so on, it's more, this sort of helps protect a little bit from things like that.
Mm-hmm.
Okay. Okay, so let's just now talk about actually doing something with the data. So here we built an LFP processing pipeline. This is a little bit of it. So this has two new elements that I want to talk about. The first is this analysis NWB file. And this is a little bit similar to what Tin was talking about. But one of the challenges we have is we often want to do pre-processing or analysis where we want to save the results. And so an obvious example of this here is local field potential, where you want to take, for us, 30 kilohertz raw data. We want to pick out a set of channels that we want to take LFP on, and then we want to, say, filter them in some band, right? This is a very common thing, or maybe we want to compute a spectrogram, or we want to do anything else where we've done some processing of the data that we want to then save and use. So again, that's where DataJoint really excels. And so this analysis NWB file relates back to the original file, and it contains a copy of the key metadata. So there's a function that creates this, so that's done for you. You just say, give me a new one. It copies the key metadata, but it doesn't copy the data. It doesn't copy the data objects, which means that this is small where this is large. And so that's really nice, because now I can stick new things in this. And if I wanted to say, send this to a collaborator, I can just send a part of my analysis, or I could merge a set of these analysis NWB files into various things and send that to someone or share that online. And it has the metadata that you need to understand where it came from. And I think this is one of the things, again, that I think, you know, as someone whose lab is involved in more collaborations than I can count, we really need an easy way of sharing this stuff, even if we can't share our whole database. And, you know, I happen to work in a medical center, which is incredibly, profoundly paranoid about computer access, because they don't want people getting access to patient data, which is understandable. So I cannot let people from the outside of UCSF get into our database. So we need a thing where we can easily share these files and the code that creates this, and then other people could populate it and duplicate what we have very easily. So that's kind of what we're aiming for here. Okay.
And this analysis NWB file is a NWB file type, or was this invented by you?
Yeah, it's another NWB file. It follows all the NWB file conventions. It just has less stuff in it than the original. So it's basically a duplicate of the original file with the big data things thrown out.
Okay.
Does that make sense?
Yep.
Okay, and then we can add something to it. So in this case, we have another thing where we pick out, and I'll show you this in a moment, we pick out a set of channels for LFP, and then we filter them to create the LFP, and then the LFP data is stored in an electrical series object in the analysis NWB file. So basically, just like the raw data is in an electrical series, the LFP data is now in an electrical series. So again, any function that can work on an NWB electrical series can work on these LFP data, and it takes advantage of the same electrode structures and tables and everything else so that it basically, the references to which electrodes it is and so on is preserved. All right, and I'll show you how that works. I think we'll have time to go through that if people are interested. And then this is a little excessive, but this is sort of as far as we've gotten right now. This won't make any sense, but I just want to give you a sense. So the idea is we would have things like position. So this is the position extracted from our video, and we might have a speed thing, which we will extract from the position. We haven't done that yet. We have digital I/O events that we get from the data. We have the raw data. We have task-related information and video files for each task epoch. We have LFP and which LFP, we have our sensor data. We have the electrode table, so which electrode was in which brain region. And then over here, all of this is for spike sorting. So we have a sort group which says which electrodes get sorted together. And all of this is in different schema. That's in this spike interface one, but I just want to show you. We have sort intervals. You might want to sort on particular chunks of time. And that's all stored in the database and it all sort of managed for the user, which is just, again, a very powerful capacity of DataJoint. We have the spike sorting parameters. This is another thing that is really important, I think, is knowing what parameters were used for every pre-processing analysis and every analysis. And DataJoint makes it really beautifully easy to create these sets of parameters and store them. You know, in a perfect world, we would also, as Tin mentioned, have ways of exporting all of this to NWB. We can actually do a lot of that now because NWB has something called scratch space where you can store different objects. We haven't implemented all that, but this idea of keeping these in parallel, I think, is really important. And then again, you can see just all of these various things, analysis files, spike sorting parameters, sort group, and so on. Okay, so that's as far as we have gotten on building this. We have a lot more to do. But I guess I will say, you know, if anyone is interested in this, if you can build an NWB file of your raw data, you probably could adapt this relatively easily, I think, to work by just commenting some stuff out. The thing that, for example, you might have to comment out is we have a probe schema, which tells us where our probes are, where the electrodes are on each probe in the NWB file, and we import that now. And so you might need to comment that out or something. But this, in theory, I think would be usable. And then I'll just, in the interest of time, I guess I'll pause here. Any questions on this so far beyond what's been asked?
Excuse me.
Yeah.
Hello?
Yes.
I have a question. Can you explain about this or different lines? Because this looks very interesting and complicated.
Yes, it is. Okay, I'm sorry. So basically the lines are just indicating which things are primary keys, that's in which ones define uniqueness. So for example, the session is the unique thing for many of the other kinds of data. So like raw data has a solid line that you can see here to session because it indicates that the session is the primary key. It's the thing that makes the raw data unique. The dotted lines are non-unique things. So dotted lines are, you have just an interval list, for example. LFP data has an interval list, which defines when it's valid, but that's not the thing that makes LFP unique. It's the selection here of which data are critical, which data go into the LFP. So this is just something you actually set up when you write, in this case, the Python code that creates all of these things. And this is just how the DataJoint folks have decided to diagram it. Does that answer the question?
Yes.
Sort of. Yeah, okay.
Okay.
Can you ask another question that will help me answer it better?
Thank you.
Okay, yeah, and I think this is, again, I think, you know, Tin mentioned that they have this nice DataJoint tutorial. If you work through that, you start understanding what these things mean. But you know what, I wasn't planning to do this, but I'll just do this quickly because what the heck. Let's see, sorry, I'm looking for a particular file and I'll zoom this in just a moment. Okay. So this is the code, and I'll make this bigger. This is the Python code. And again, if you don't know Python, this is not going to be helpful. And I realize this is, okay. So this is the function that defines, and let me get rid of this thing, an NWB file in DataJoint, all right? And so at the top, you have a little string, and this definition string is what DataJoint uses to say what's going to be what. The things above this little three dashes are the primary keys. So this says you have an NWB file name, and that is the thing that makes each NWB file unique. And then you have below that an absolute path, which is not unique. So if they were drawing this, the NWB file name in this case, it's not relevant, but this would be the thing that is specific. And I'll just show you one other thing. So now that we have this NWB file schema, and I agree, so you just sort of have to work with this, we can have a session schema, all right? And in the session, this little dash arrow means it depends on the NWB file. So this goes back to the NWB file and says, hey, what's the thing that makes an NWB file unique? And it uses that as the thing that defines this table. So once you get used to writing these things, you can sort of fairly easily say, okay, this depends on an NWB file as the thing that makes it unique. But it also relates to a particular subject that I might have a table for, a particular institution, and a particular lab. And again, if that doesn't make sense, that's totally reasonable. It took me a while to get my head around this, but the tutorials are really very good. So if you're interested in doing this, definitely start there, and then this code hopefully will make more sense. All right, hopefully.
Maybe related to this diagram you showed before.
Yep.
Could you just quickly say, like, is every little rectangle and circle a data file that you share?
Oh, I'm sorry. Yeah, great question. These are database. Oh, sorry.
What's the difference between the blue and the green?
Yes, okay. First question, these represent database tables. So it's just a list of stuff. It's not a file. It's a thing in basically, I mean, it's stored in the database, but it's just a table. And what that means is it's a list of things that define a session or a list of things that define the raw data. Now, some of these also correspond to NWB files. So the raw data, for example, has a reference. You can follow this here. It depends on a session, and the session, I'm going to go over here, depends on an NWB file. So the raw data has access to the NWB file that the raw data is in, which means if I go to this raw data object and I say, hey, give me the raw data, it can follow that back to the raw data, to the NWB file and pull out the data. So there's a small number of files here, like almost most of this is one, well, there's what's represented here actually is a total of 3 files. One is the raw data file, one would be an LFP file, and one would be a spike sorting output file. So not so many files on disk for lots of data structures that organize them. Is that clear enough?
Yeah.
Okay, thank you. No, and Sylvia, thank you for the questions. I really appreciate them. The other question you had is about the differences in these ovals versus rectangles. So this is a difference in just how you stick the data in. And it doesn't really matter for today, but the basic idea is these things, the data are inserted by hand. So you manually do what's called an insert call, and this is written into the code to look in the NWB file and insert an institution. The blue ones are done automatically through what's called a populate call. So they have a function in them, a method called make, and that make automatically looks for what's called the primary key, and for every primary key, like every NWB file, it puts the stuff it needs in the session automatically. And I can show you what that code looks like, but I'm guessing that might be a bit much, but let me know if you'd like to see it.
I think for now that's
okay. That was my intuition, but I wanted to check. Okay, so let me show you one more thing in the interest of time is how would we get LFP out of this? All right, so let me switch to this tutorial. Okay, this is the NWB DataJoint LFP tutorial notebook. So again, we load up some modules. Most of that is what I showed you before. Excuse me. This is the specific extension we have for our special NWB objects that we use. If you're using an NWB file that doesn't have these, you don't need that. Okay, and so now let's say I want to, in this thing, I want to extract LFP from a set of channels. So it turns out the data that this is from 2 128 channel polymer probes that are in one of our rats. And so we might have many rats, we might have many days of data. In this case, we're just going to pick one because that's all we've stuck in our database so far, but we could have many. And so we're going to pick an NWB file. And so here, this would give us a list of all of the NWB files by name. And so here, we're just taking the first one of those NWB files, and that turns out to be this file. It doesn't really matter what it's called. This is just the one that Ryan made for this purpose. Now, what we now do is we do some things for filtering. Many of these only need to be run once. So we have, for example, an FIR, finite impulse response for the aficionados filter, and we create some standard filters. So these are filters that my lab uses, and really all this is LFP filters. So I just want to bandpass the data between 0 and say 400 Hertz. All right, so what are the things we need to do? What we can do is think about all of the steps we have in creating, say, local field potential data. Well, first, which electrodes do you want to use? Do you want to use all of them? Do you want to use a subset of them? And you really want this to be flexible. So what we can do is we can get, well, what are all the electrodes we have available? So we can fetch all of the electrode IDs for our electrodes. All right, and we can fetch this specifically for, in this case, I'm being sloppy because there's only one set of these in the file. Normally, we'd fetch these for the NWB file we're talking about. And then let's pick a set of them, which are the electrode IDs going from 0 up to however many they are, every 16th one. All right, and then we're going to run this thing where we have this LFP selection, and we're going to set those electrodes. So this is the NWB file name we're going to use, and we're going to create a list of these electrode IDs, and I'm just going to show you what that looks like now. So it doesn't really matter if this makes complete sense or not, but if you just get the idea, we just want to pick out some electrodes. So we just need their numbers, and then we stick them in this table. And so here's the table. We have an LFP selection table, which has what's called a part table inside it. And that is for this file, we have electrode groups, which I'll talk about in a moment, and electrode IDs. And so what you can see is we've picked every 16th electrode here. All right, and so we've just stuck this data in a table. And now this table tells us which data to use for our LFP. And the nice thing is you can just look at it, right? And you can change it. You can delete entries, you can add entries. Just note the electrode group name here. In this case, this corresponds to which physical device we used in the brain. So electrode group 0 is the first 128 channel probe, and electrode group 1 is the second 128 channel probe. And you see there's sort of more lines that aren't shown. Okay, so now we have this table, and again, this gives us, we can't lose this anymore. If we deleted a line from this table, it would delete all the stuff that depends on it, as Tim mentioned, which is really powerful so that you can't mess up your data, basically. Okay, then all we do is call this populate command. So this automatically creates, this is a new analysis NWB file. This uses some code from a package called Ghost2Pi, which allows you to do the filtering out of RAM. For us, we tend to have big files, so we don't necessarily want to load 100 gigabytes of data in at once. And then in this case, this is a very short data file, so it doesn't take long, but I'm still not going to run it. And now, now we have LFP data, all right? And it's only for these channels, and that's it, all right? And so I like this because, oh boy, it's simple. Once you have set, once you know which filter you want to use, and that's sort of defined in this LFP thing, sort of hard-coded in this case, off you go. All right, so once you've got LFP, you usually don't stop there. Like in my lab, we often we filter for other bands of interest. Lots of labs do this. So here we're just going to create a filter for something that we might want to use. All right, and so filters, as you may know, are defined by the sampling rate of the data and their band pass and band stop characteristics. So here we can just say, okay, look, what's our sampling rate? So let's get the LFP data for this NWB file and get the LFP sampling rate field. Great, now I know the filter. Now that I know the rate, I'm going to create a new filter that I'm going to call my 5 to 11 Hertz data. And I'm just going to add this filter for this sampling rate. This is the kind of filter it is. These are its characteristics that I want. And this automatically creates the filter and sticks it into our new table. And so this then shows you what that table looks like. These are all the filters we have at the moment. And of course, users can add any number of these. We have these 2 previously created LFP filters just for the 2 sampling rates we tend to use. And now we have this new theta filter, which is for basically where we want to downsample the data, because we've done LFP downsamples it. We don't need full 30 kilohertz data. And then we have these low stop, low pass, and so on and so forth. And then finally, we have these what are called blobs, which are just NumPy arrays, which have information on what the filter's characteristics are. And then these are the coefficients for those people who know about filtering. All right. Now, maybe we don't want, oh, please, yeah.
So just to understand like the workflow of analysis. So am I right in guessing that you wrote this filter function? Like this is your definition. This is kind of your personal analysis you want to do, and you, yeah, I'm not quite sure how you put this, because this NV was like the database, right? Yeah, I'm confused.
Sorry, Sylvia, I missed that. So yes, like the FIR filter thing, I wrote that. I can show you quickly what it looks like, but it's a table in this case, right? So it's another DataJoint table, which just has this information in it. Now,
so I guess at some point you will actually filter the data.
Yes, right. And so there I'm taking advantage of a package that does the filtering. And again, I'm happy to show you these things, so let me know. But let me walk through a little bit further and let me know if this answers the question. Okay. So, okay, now again, we often want to do a second set of subsampling when we do the LFP band filtering, because we might not want every electrode. We might want some specific ones. So we're going to pick the first three that we've got of LFP, which turned out to be 0, 16, and 32. And I'll just go up here a little bit. You see, we have, these are our electrode IDs. So those are the ones that are available to us, because we have to have LFP to do this. And so we're just going to pick the first three, right? You could pick any subset of these. Obviously, you can't pick ones that you don't have LFP for. What times do I want to do the filtering for? So here, I'm going to use a predefined interval list, and I haven't shown you this, but this is the name of one of the sets of times that we've created. This happens to correspond to the first epoch, which is the first sleep session for my lab. Sometimes you want to use a reference electrode, right? So you want to subtract off some reference, so you can specify that. In this case, we're just not using it. And then tell me what output sampling rate you want to get. So in this case, we sort of said, let's make it about 100 hertz. Okay. And this doesn't really matter, but this is just showing you the time of that interval. And what we're going to do next is we're just going to set the electrodes. So just say, I want to use these electrodes, this interval list, this reference, and so on. And that's what this new LFP band selection table has. It's interval list name, sampling rate. This refers to, then this has a subset of things in it, which have one entry for every electrode you want to filter. In the interest of time and people's sort of mental status, I'll skip that. Oh, actually, no, I won't. I'll show you here. So these are then the lists for this particular 1000 hertz thing of which electrodes for this filter, what sampling rate and which electrodes do I want to use and what reference did I use. So again, it's just keeping all this information in a really easy form so anyone could go back and see it. And then finally, I'll skip this in the interests of time. This is just the LFP data that we're grabbing. But to get, Sylvia, to your question, this is what does the filtering. So LFP band is a function that I wrote, but on top of a filtering package. And what this does is it goes through every one of these electrodes. It actually filters them all at once, but that's not not critical for this. And it runs the filter that we've defined on those electrodes, all right? And so if you look inside this code, you can see exactly what filtering operation is done. And of course, you can add your own, right? You could change this populate function. You could put if statements in there to do it with different filtering packages and so on. But again, what I like about this approach is on one hand, it exposes all of the filtering parameters, right? So you can't lose them. You can't not know what filter you use. You can always go back and do that. So if you ever do something where the frequency of response of your filter matters, you've got it right there. every data point is associated with this filter. At the same time, if a user doesn't want to write their own damn filtering code, they don't have to, right? And in some labs, everyone writes their own code, which is slightly nutty. This is just one function that everyone in my lab, and again, perhaps everyone in other labs could use, that will create LFP data from a particular band on whichever ones they use. And it's very easy to swap in and out the specific computation inside this, or to make variants of it and things. So that's quite straightforward. And then I'll end, just because I imagine people are pretty tired at this point. What does this buy you at the end? Okay, so let's actually look at a little bit of data. So, one thing that actually can kind of be a pain is just getting different kinds of data together on top of each other. But the nice thing here is all of the times are always referenced to the same thing. So time is absolute, as I mentioned before. The electrodes always reference the same thing. And so I'll skip the details here, and I'll say all of this stuff that I've written here could be like one function call to a plot electrical series function, which I'm guessing Ben or someone has written, but I haven't taken advantage of yet. So if you just said, I want to plot these electrodes in this electrical series at this time, that's all that this code does that I'm showing you right here. So I'm just going to skip over that. But the upshot is I can plot the original electrical series, which is the raw data, the LFP, which I've downsampled from it, and the LFP band downsampled from that on top of each other, right? And that's not typically particularly easy to do. And again, with a single function, theoretically, this could be like 3 lines of code to actually write this thing, although you need to specify the times. And so for us, I guess just having access to all of these data, being able to go back and forth, having them all reference together to the same thing and having them easy to get to, I think will make things a lot easier. And again, the same thing, adding spikes on top of this just means you'd go over to your spike sorting schema and take the output of that and which units you want and plot them on top. And so because they're all referenced to the same NWB file and the same time series, I think this has the potential to make analyses much faster, more accurate, and sort of more reproducible, which I think is really key. All right, I will stop there. I appreciate your attention and your questions. I'm going to skip the spike interface.
Sorry, can I ask a quick question about the filters?
Yeah, please, Alessia.
You mentioned you're using a package that does everything basically on the file, right? Is it called ghost.py?
Ghost.py, yeah.
Could you please paste it on the chat, because we're also trying to basically improve the performance and the efficiency of the filter. Basically, I think it's one of the main bottlenecks in.
Yes, so I will say this package works really well. So here we are, and I'm going to, let's see, where did it go? Oh, you know what, I think it's part of NumPy. So sorry, I'm just trying to, I believe it's called Ghost. Sorry. I don't remember why he called it this. So what this does, it's not as fast as I wish it were, but I'm going to paste it in now. But what it does do well is, sorry, and now I'm looking for the chat, which I am not seeing for reasons I don't understand.
Yeah, I found it. I can paste it.
Okay. So what this does nicely, and again, all the code I wrote makes use of it. So the person who wrote it, I worked with to get this working. It does, as I mentioned, out of RAM. So it reads in a chunk of data. It's not as fast as I wish it were, and I think it could be made more efficient. But is it nice not to have to load 100 gigabytes of data, right? And I think that's really
no, of course. I mean, we have the same in Spike interface, like filtering in chunks, but it's hard to make it efficient.
Yeah, well, take a look at this, and if this is better, or again, I would be very happy to replace this with the Spike interface filter calls.
Yeah.
Right.
No, we also have, just so you know, we also have this in-memory filtering, so you can just basically do it on chunks. But another question is there a particular reason why you use finite impulse response filters instead of like IIR? Aren't they like a bit slower to run?
They can be a bit slower. I don't know why it's
you don't have any distortion, I guess, but does it actually make a difference in LFPs, right?
Yeah, so I don't think it really matters. So indeed, FIR filters tend to have, for the same frequency response, have a larger number of coefficients. On the other hand, you can run them because they're linear in phase. You can run it once through the data, and you don't need to phase compensate by flipping the data and running it back. So from that, in that sense, the IIR filters are not always a win. And so, you know, for the most part, the filtering for us has not been the time killing. I mean, it does take a while, but we just tend to do it and then it's done. So we haven't like focused on it as, oh my gosh, this is the key thing that we need to speed up. Whereas like other things for us, like clusterless decoding, oh my God, those are things that we need to speed up. So that said, I would love to have it all go faster.
Yeah, we're thinking about the ways to improve filtering efficiency. And one thing that might be a bottleneck actually also in the NWB format, it's the order of the data, right? So instead of, I think we should switch to like a time times channel. That would make it much easier to chunk and to like parallelize different chunks on multiprocessing, right?
Time by, you mean each channel alone, instead of having a big array of channel at a given time point?
Yeah, exactly. No, sorry, not that. But I think now both NWB and like other formats, they prefer to have like basically channel one, basically n channel times number of timestamps, right? And that makes it a bit more less efficient if you want to chunk by time intervals, right?
Oh, because the time steps are on the wrong axis.
Yeah. So instead, if you had like the transpose, you would just basically have one file seek and get the entire blob of data, and you know, like you're chunking right.
Understood.
So we think actually this could help a lot, but we're still discussing about that.
Yeah. And I guess, you know, these are all of these things. This is a question of what are the pain points, right? So what are the things that are worth a lot of people's time? And you know, for me, I will say, like, I think this is for me, this is sort of a game changer in terms of what we can do. But for example, we've run into this challenge that the Python H5Py library is not good at getting little chunks of data and lots of them.
Exactly.
Forever. So you have to load up all the data into RAM, get the chunks, and then load up the next data, which fine. And, you know, I know the NWB folks are working on a ZAR backend, which might solve that problem. Lots of these things, you know, that honestly I had no idea about, and I kind of wish I still didn't. But there you are. So, but they're solvable problems. And I guess I'll just sort of, you know, put in as at the very end, this is the last moment of the workshop. So, you know, if we could all get on the same page, nothing is perfect and nothing will make everyone happy ever. You know, you realize that when you've worked with a lot of people, it's just impossible. But if we can get on the same page, at least as far as format, then the tools work from the format, right? And then it's easy. Or a set of formats and a set of tools like Spike Interface that can work with many formats. Just more things like that, I think, are really things that the field needs. And so, you know, I just want to encourage people to take the time to do it, even though it's painful and it takes a long time to retool a lab. You know, and I'll just say, like, you know, I've been working on this a lot in these pandemic times because I'm stuck at home, which has been sort of, you know, trying to make a silver lining out of this cloud, and that's been helpful, but it's really hard, right? It's a huge amount of work to redo the sort of analytical pipeline for a lab. But if you actually do it, the benefits are huge. So I hope people will take the time to actually do it, because I think 10 years from now, if you do this for yourself, you will be happier. All right. Any other questions on this or anything else?
Yeah, Loren, I've got a question about, you mentioned this cachery method of storing your data, I'm assuming your raw data.
Yeah.
So when you call that fetch command, is that downloading an entire raw data, like a huge NWB file from cachery right now?
Right now, no. So right now we're still in the early stages of this, Ben, which is a great question. So one of the things, and just for everyone's reference, like downloading huge data from somewhere online is a terrible idea, which you never ever want to do, right?
Yeah.
So in our case, we have the data on our local RAID file server, and the cachery is a local instance. So if we wanted to load it, it would just grab it directly from the hard drive. The advantage of the cachery is that it would mean that I can point someone in another lab to one of our analysis files, which is small. And I can just share the hash of that, and they could grab that file from our server without a problem. And so that's the idea. Or, you know, maybe we'll eventually, I mean, obviously we'll eventually upload a lot of these things to the Dandy archive, things like that, but we're not there yet. And our analysis files are still quite specialized and sort of make sense in the context of the whole DataJoint thing. So we're playing with this as a way of sharing within our collaborations. And also Jeremy is working on sort of a curation, spike sorting curation tool, LabBox eFizz. So we're sort of working with him to test that out and see if we can use that for curating the spike sorting from spike interface, because we need to do a few things that are not, you know, part of that package yet. So, and that communicates via cachery. So that's where we are.
Yeah, so if you're interested in reading segments of data, kind of reading data lazily from cachery or from another cloud service like an S3 bucket or Google Cloud, we're working on technology that allows you to lazily access HDF5 data sets directly from a remote site. So you wouldn't then have to download the entire raw data if you just want an interval. And you could iteratively read it, and you could even parallel access it to do parallel compute over it.
That would be awesome.
If that sounds like it would be useful for you, we should talk about.
Yeah, that would be great. I mean, you know, right now I'm focused on getting something working in my lab.
Yeah.
But as this expands out to collaborators in other institutions, that's exactly the sort of functionality we need. So that'd be fantastic, Ben. And sorry, Alessia, did you want to add anything?
Yeah, so I just wanted to add that if you need some or if you develop some tools for curation and stuff, it would be great if you could basically add them back to Spike interface, because I think this would make it accessible to many people. And
totally agree. That is absolutely the plan. And it's Jeremy, right? So you've worked with Jeremy.
Yeah, of course.
You know, so yes, we would very much like to do that. It's just it's not there yet. It's basically still in the developing views stage. And I hope this will work, because we need to be able to curate our data, but we don't have anything to show yet.
And just so you know, also Cyril Rossan, the developer of Phi, is working on a web-based version of Phi. So we shouldn't duplicate efforts, I think.
That's great.
And I think what you could do if you had a web-based version of Phi or something like that, you could start collecting user data and to make it automatic, right? Say after 3 months of manual curation, we know what humans do, right? So we could just do our
I guess, absolutely. I think, yes. I mean, this is a whole other discussion about how one
of course.
I think, yes, that all of that sounds really great to me. I just have limited bandwidth, but if that's out there,
we should coordinate. There are different efforts, and
that would be nice.
Much better if come together
and as long as it takes advantage of Spike interface recording and sorting extractors, it should be straightforward, right? So that's great.
Okay.
All right. Okay. Look, I appreciate everyone's attention. Go have dinner, or get a drink, or whatever it is. For those of you who are actually in Europe at this time, and good luck with all this.
Thanks so much, Loren. I think it's really great that we're really taking these ideas of integrating DataJoint and NWB and really showing that it can truly be done in a lab, and it can really make everything